I'm going to offer you a bet. You'll start with $100. We'll flip a fair coin, 50-50. Heads, your money increases by 50%. You now have $150. Tails, it goes down by 50%. You're now down to $50. A 50% gain versus a 50% loss. Equal odds. We'll play this game 500 times. What do you say? Would you take that bet? Take a second and think about it. Seems fair, right? Plus minus 50% return, same chances. You'd expect to end up roughly where you started. Or is it? What if I told you that starting with $100, the chances of you finishing with at least $1 remaining in your pocket are 1 in 53 million? More striking still is the fact that the chances of you having made any money from this game, that is, you ending up with more than $100 in your pocket, is a whopping 1 in 427 million. You have better odds of winning the Powerball lottery jackpot than making a single dollar from this seemingly fair game played 500 times. Let's do what mathematicians do. Calculate the expected value. This, as the name suggests, is the money you should expect to have by looking at each outcome weighted by its likelihood. Since here there's a 50% likelihood of winning, and winning yields $150, you should put that down as 0.5 times 150. Similarly, the likelihood of losing is also 50%, and losing leaves you with $50. So you put that down as 0.5 times 50. This simplifies to $100. This is the reason why the game feels fair. The expected value is indeed $100. We can actually take this further. The expected value doesn't change no matter how many times you play. Here I'm showing with 2 games and 4 outcomes, but no matter if you play 10 games, 100 games, or a million games, the expected value is still $100. So let's test this out. We play twice, you get 1 heads and 1 tails. Seems fair. You broke even, right? Let's check. 100 times 1.5 times 0.5. That's $75. What about tails first, then heads? 100 times 0.5 times 1.5, still $75. The order doesn't matter here. 1 heads and 1 tails in any order always leaves you with 75 cents on the dollar. Play 2 more rounds, 1 heads, 1 tails. Now you're at 56.25, then 42.19. Each pair of a win and a loss actually sinks your wealth by 25%. Confused? Here's what's happening. When you gain 50% and then lose 50%, your brain processes that as a plus 50 and minus 50. Net, 0. But you're not adding and subtracting. You're actually multiplying. 1.5 times 0.5 is not 1, it's 0.75. Think of it like this. A single loss cuts your money in half. So in order to get back to where you started, you actually now need a 200% return on the remaining amount, not 50%. Essentially, each loss in this game is roughly equivalent to 1.71 wins. Hardly fair. But wait, if this is secretly a losing game, why does the expected value tell us it's neutral? Let's simulate. 1,000 people, each starting with $100, each flipping independently for 100 rounds. Let's take the average wealth of the group afterward. It's still $100, exactly the same as what we started with. Expected value was right, except let's look at the distribution of this wealth. What we observe is that a very small handful of exceptionally lucky players actually end up with most of the wealth. Someone who flipped heads 70 times ended up with roughly $200,000. And players like these pull the average up to the expected value. This is similar to the math joke of a billionaire walking into the bar and telling the barkeep he just 1000x the average net worth of the room. In situations like these, it's actually better to instead look at the median player. 50 heads, 50 tails. Their wealth is 100 times 0.5 to the 50th power times 1.5 to the 50th power. That's 1/2 of 100th of a cent. Over 95% of players have lost money. The average might be neutral, but the most likely lived experience of a typical player is absolute ruin. In a 100 game scenario, this is what the distribution of probabilities over the number of heads flipped looks like. The break-even point of 63.1 heads is all the way over here with a probability of 0.26%. And this is how wealth evolves for a typical player versus a lucky player who happens to flip heads 90% of the time. This isn't just a hypothetical math puzzle. This is the structure of any system where outcomes compound on your current state. Leveraged investing, repeated risk taking, career bets where failure shrinks your runway for the next opportunity. Anytime the result of one round becomes the starting point of your next, you are playing a multiplicative game. And in a multiplicative game, the average outcome across many people tells you almost nothing about what will happen to you over time. Just as the expected value in our coin game tells us what the ensemble average will be if many people played this game, but tells us nothing about what the typical player will experience. There's a word for this distinction, and understanding it changes how we think about risk. The concept is ergodicity. A process is ergodic when the time average, what happens to one person over many rounds, equals the ensemble average, what happens across many people in one round. Roll a fair die a million times, your average converges to 3.5, same as the group average. That's ergodic. Each roll is independent. It doesn't act on your previous result. But in our coin game, each flip multiplies your current wealth. Your path depends on every flip before it. The path dependence is what breaks ergodicity. And this is why a stroke of bad luck changes everything. This is why it's so hard to bounce back up on your feet. In an ergodic system, a bad outcome is just a bad outcome. Play long enough and you will recover towards the average. In a non-ergodic system, a bad outcome can be permanent. No sequence of 50% gains can bring you back from losing everything. This is why insurance makes rational sense even though the expected payout is negative. So if expected value can mislead us, what should guide our decisions? Well, instead of maximizing the average outcome, maximize the average growth rate. There's a formula for this. It's called the Kelly criteria. The full details of this formula are perhaps best explored in a future video. But know that for our coin game, it says do not bet. You cannot win this game no matter how hard you try. If, however, we were playing with a biased coin that produced heads, say 60% of the time, we would be best off betting 20% of our wealth in each round, enough to capture the upside, but small enough to survive the downside. So while the full bet player's trajectory collapses to zero, the Kelly player's trajectory wobbles, but ultimately goes up. So what's the takeaway here? Ergodicity is the hidden variable behind some of the most important decisions you'll make in your life. It's why go big or go home, in the face of good odds, is actually terrible advice if the loss will be irrecoverable. So next time a big opportunity with a great payoff shows up, don't put all your eggs in the one basket. Save some for when the basket drops.